So with this first category of levers or machines, we go to the second category of machines, that is pulleys. What exactly is a pulley? Pulley is nothing but a solid circular disc that is fixed about a rectangular frame called the axle, fixed to a solid rigid support and free to rotate, having a circular groove around its periphery, which carries a light inextensible string. Both the ends of the string are used to apply the effort and the load. One end of the string lifts the load. The other end of the string is the one which we are applying the effort. So we see a pulley over here. The one which we show here is a single fixed pulley. Doesn't this figure sound similar that you must have seen somewhere in remote villages? Definitely you must have seen people drawing out water from a pulley, from a well, wherein you see that the pulley is being utilized. Let's see how this pulley works. We are having the load at one end. We are applying the effort at the other end. The load is being lifted against gravity. At the same time, the effort is applied towards gravity. So we get the convenience in direction. And since we get the convenience in direction, we always use it as a simple machine. If I talk about the mechanical advantage, I know whenever there is a stretch in a string, there is a counter-reactive force called the tension in the string. So when I apply force on a string in terms of load, there is a counter-reactive force called the tension acting upwards. When this counter-reactive force acts upwards, we see that this tension is balanced by the load. Similarly, at the other end, I have the effort that is acting. This effort is also acting downwards towards gravity. So it will also have the component of tension in it. That means the load is balanced by tension. Effort is balanced by tension. We have mechanical advantage for a single fixed pulley as load upon effort. That is tension upon tension. That is equal to 1. That means whatever force I have applied is equal to the load that is being lifted. With this, I see that mechanical advantage is 1, but because I am getting the convenience in direction, I definitely can utilize it as a simple machine. The second way, or there is a application-oriented question on this, which states that prove that a single fixed pulley is a modified form of class 1 lever. How do I prove it? We have a free body diagram which can turn this pulley into a class 1 lever. The fulcrum is the point of rotation. So I see that the point at which the pulley is free to rotate is the fulcrum. The load point is the point where the string is tangential to the pulley at the left end. The effort point is the point at which the string is tangential to it at the right end, diametrically opposite end. So I have the load, the fulcrum in between, and the effort. Which class of lever does this be? This is definitely going to be class 1 lever. So with the free body diagram, I can always show that single fixed pulley is a modified form of class 1 lever. Another way of determining the mechanical advantage. As I said, mechanical advantage is definitely load upon effort. At the same time, it is also effort arm upon load arm. Looking at the modified free body diagram, what is the effort arm in this case? It is the radius of the pulley. What is the load arm of the pulley in this case? Also the radius of the same pulley. Since radii of the same circle are equal, we have effort arm upon load arm equal to radius upon radius, that is equal to 1. Let's consider the second type of pulley, that is single movable pulley. Now this single movable pulley reminds you of a particular toy which you must have seen in your kinder ages. You know what it is called? It is called as yo-yo. I'm sure you know what yo-yo is all about. However, this is not yo-yo. This is definitely a single movable pulley for that purpose. But then in a single movable pulley, we have a fixed string and we have the pulley that is attached to it and we have the effort string that is acting in the upward direction. Remember here, the effort string is in the upward direction. And the load is connected with the pulley, and it is that which is being lifted along with the pulley in the direction opposite to gravity. Definitely one will have a question in their mind, why should I lift a load if I have to lift it along with the pulley and against gravity? Your thought process is perfectly correct. That is why we say that this type of machine is an impractical machine. But however, we study it as a class, because then in the third class, we are combining the first and second put together. If we talk about the mechanical advantage for this, the mechanical advantage works out to be load upon effort. And now this load is catered to two tensions that is there in the strings. So we have twice tension upon tension because of the effort. So 2T upon T, that is equal to 2. What is the significance of mechanical advantage being equal to 2? It only indicates that the effort required is half the load. So we are getting an advantage in the force. But what about the direction? Are we getting the convenience and direction? Definitely not. What we are seeing is that we have to apply an effort against gravity. As a result, it is an inconvenience to the person using the machine. And hence, we avoid using such type of machine. In terms of another application-based question on this, we can say that prove that a single movable pulley is a modification of class 2 lever. The first one was class 1 lever. Here it is class 2 lever. If you observe the pulley carefully and it's working, we see that the pulley basically keeps on rotating about the fixed point that is along the vertical string. This particular point acts as the fulcrum for the pulley. The load is attached at the center towards the axle. The effort is applied at the extreme end, that is the diametrically opposite end. So what is the effort arm in this case? The effort arm in this case is the diameter of the pulley, whereas the load arm distance is nothing but the radius. So we have the mechanical advantage in this case as effort arm upon load arm, that is diameter upon radius. Diameter is nothing but twice the radius upon radius. Radius cancels, so we are left out with 2. So mechanical advantage for a single movable pulley is 2. But as I said, it is inconvenient to use it because of the direction that we are applying. So we use this in combination with a single fixed pulley to get the third type of pulley, that is combination of single fixed, single movable. In this case, we see that due to single fixed, single movable, we do get the mechanical advantages too. At the same time, we are getting the convenience in direction. So the point of application of effort is bringing it towards gravity. At the same time, because of the movable pulley, we are able to lift the load against gravity. So we are getting both parts, the mechanical advantage equal to 2 and convenience in direction. However, these are simple machines that are used to lift smaller loads. But at times we are required to use heavier loads. Like in case of hoist, industries, we use Jib Cranes, which you must have seen definitely. Now these utilize a combination of pulleys. The combination of pulley is categorized as block and tackle. The block is the fixed part and the tackle is the movable part. In block and tackle, we have two classes again. One is for even number of pulleys. The second is for odd number of pulleys. Odd numbers are 3, 5, 7. Even number 2, 4, 6. Let's consider a block and tackle for odd number of pulleys. The thumb rule that we apply here is that the number of pulleys in block is one more than the number of pulley in the tackle. That means if there are 5 pulleys in the total system, number of pulleys in the block is 3. Number of pulleys in the tackle will be 1 less, that is 2. Supposing we have 7 pulleys, it will be 4 in block and 3 in tackle. So when we consider a system of 5 pulleys, we have to draw a diagram for the block and tackle? While drawing the diagram, we follow certain steps and care so that we draw the diagram carefully. First step is to draw the solid rigid support. Then we draw an axle, that is a thin rectangular plate, in which the length of the tackle for the block is definitely more than that for the tackle. Then we start drawing the pulleys. Pulley with the largest diameter is drawn towards the rigid support. Its counterpart is taken at the farthest end of the lower block. Second pulley that we draw is having a considerable large difference in diameters as compared to the first. It has its counterpart at the second part over here in the lower block. And the last one, that is the baby pulley, works out to be in the block. After drawing the pulleys, we have the hook for the block and we have the hook for the tackle. Then comes your main part, that is tracing the path of strings. Now in case supposing we do not know from where we have to originate the strings, let's consider that we are starting the string from the hook of the tackle, that is the lower block. For a block and tackle system wherein we have the number of pulleys in the block more than the number of pulleys in tackle, the string has to start from the lower block. When we have the string starting from the lower block, we trace the strings as shown earlier and we see that the effort string comes out from the last pulley. This is how we go about for even number of pulleys, wherein the number of pulleys in block and the number of pulleys in tackle are the same. So the first pulley drawn, its counterpart below, second pulley drawn, the same counterpart below. And then the string starts from the fixed block, that is the block at the upper end, and we trace the string so as to get the effort. Always in case of block and tackle, we remember that the velocity ratio is equal to the number of pulleys. So irrespective of whether it is 6 pulleys or 4 pulleys or 3 pulleys, we always say velocity ratio equal to number of pulleys. If it is an ideal system, then mechanical advantage also will be equal to velocity ratio, as efficiency is MA upon VR, that will be equal to 1. But it's not the case always. We know that we are considering a practical machine. In case of a practical machine, we always see that mechanical advantage is equal to load upon effort. With load and effort given, with the velocity ratio known, we can calculate the efficiency of a block and tackle system. Let's consider the third type of machine, that is an inclined plane. What exactly is an inclined plane? Well, the today's generation is all hip, all into the Western culture. You must have gone to various shopping malls and you must have seen a fashion parade. Do you know how the fashion parade is conducted? You have a ramp walk or a catwalk that is being done. What exactly is a ramp, or what exactly is the construction of the machine over there? If you carefully observe, it is nothing but this inclined plane. You know, when the models have to walk across the ramp, they are given a particular style of walking in a crisscross manner that entitles the posture for a person to walk through in the most possible and elegant way. But for that, we do have to take the aid of this inclined plane. So this inclined plane is a type of machine which gives you ease or convenience in direction. Similarly, another example I can give you where an inclined plane is used. If you go to a showroom, automobile showroom, and you want to take a vehicle, say a car, a BMW, and you have to bring it to the road, the showrooms are normally placed at a higher level. Now, when you try to bring the vehicle down onto the road, we have a slope that is being created. That slope acts as an inclined plane because it's giving the ease with which the car can be brought down from the showroom floor to the road. Similarly, if I have to lift a barrel up a truck, I cannot lift it straight vertically up and keep it as a crane or a robo would do it. Instead, I use an inclined plane and roll the barrel up the truck, which gives me the convenience in direction. So inclined plane is nothing but a plane that is inclined to the horizontal, in which we get the convenience in direction of application of force and the point of application of force. The mechanical advantage for an inclined plane is length of incline upon vertical height. Length of incline upon vertical height. Length of incline as far as a right angle triangle is concerned is hypotenuse upon the opposite side. Which trigonometric ratio will give you this particular ratio? It is cosec theta. And what is cosec theta in terms of basic ratios? 1 upon sine theta. So we have mechanical advantage as length of incline upon vertical height equal to cosec theta equal to 1 upon sine theta. Screw is a modified form of inclined plane. How do we say screw is a modified? You know, you must have seen screw. The carpenters use screw to fix up 2 or more objects. How do we say? Can you ever imagine that screw is a modified form of inclined plane? It is true. We can have a demonstration done for it. Why not cut an inclined plane, a right angle triangle from the piece of paper? Shade the hypotenuse. If you shade the hypotenuse, you know what this particular hypotenuse is going to give you? It is going to give you the screw threads. Are you surprised by it? Well, let's do it. Rotate this inclined plane about a circular periphery, about a circular pencil or a circular rod. See what is happening, how the threads are being generated. We see that the length of incline takes the shape of screw threads as you twirl the inclined plane around the circular periphery. So we can always say that screw is a modified form of inclined plane. We define screw as when an inclined plane is rotated about a circular periphery, the length of incline takes the shape of screw threads. So we can say screw is a modified form of inclined plane. Mechanical advantage in this case, the length of incline upon vertical height. In this case, length of incline is nothing but the circumference. So circumference divided by the vertical height. What is the vertical height in this case for a screw? It is the distance between consecutive threads, and that we have defined as pitch. So it is circumference upon pitch. Circumference is nothing but 2 pi r upon pitch. Now here the radius is nothing but the average radius. The radius at the top and the radius at the bottom.